On February 27, 2026, a spacecraft more than 15 billion miles from Earth executed a routine command, a slow, deliberate roll, the kind of maneuver it has performed without incident dozens of times over nearly 5 decades in space. This time, something in the resulting data caught the attention of the engineers watching it. Not a turn back toward home. Voyager 1 cannot do that, and never will. It is moving in a straight line, permanently, deeper into the space between the stars, and nothing about its trajectory has changed or will ever change again. But buried in the routine telemetry from that ordinary calibration roll was a power reading that shouldn't have been there, a sharp, unexpected drop that pushed the 50-year-old spacecraft closer to an automatic emergency shutdown than it had come in years. That near miss forced NASA's engineers to make a painful choice within weeks, permanently switching off one of the last handful of instruments still capable of measuring the space beyond our solar system. And in doing so, it drew renewed attention to something Voyager 1 has been quietly recording since 2017, a signal that scientists still cannot fully explain, sitting in the data from a region of space no other human instrument has ever managed to reach. This is the real story of what Voyager 1 has actually detected out there, why the specific plasma signature at the center of it remains, by the researchers' own admission, unresolved, and what a routine maneuver in February 2026 revealed about just how little time is left to keep listening. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why a single unexplained signal from a decades-old spacecraft still matters this much to modern physics, you first have to understand exactly what Voyager 1 is, and how genuinely improbable it is that it's still capable of teaching us anything at all. It launched on September 5th, 1977 on a mission built to last around 5 years, a tour past Jupiter and Saturn before falling permanently silent, according to the original plan drawn up by NASA engineers who had no reasonable expectation the spacecraft would still be functioning half a century later. Instead, it kept flying, using the gravitational pull of each planet it passed to add speed and extend its trajectory. And on August 25th, 2012, it crossed a boundary called the heliopause, the true edge of our solar system, becoming the first human-made object in history to leave the space governed by our own sun's influence and enter, for the very first time, the space between star systems. It remains, alongside its twin Voyager 2, the only spacecraft ever to have physically measured that environment directly, rather than inferring its properties indirectly from a telescope safely inside our own solar system's protective bubble. That distinction, direct measurement versus indirect inference, is the single most important thing to understand about why Voyager 1's data continues to matter so much, even decades after launch. For the entire history of astrophysics before 2012, everything scientists believed about interstellar space, the region beyond our own sun's influence, had been built from models, mathematics, and careful extrapolation from telescopes and instruments located safely inside our own solar system. Nobody had ever had a physical sensor actually sitting inside that environment, taking real, continuous measurements over an extended period of time. Voyager 1 changed that permanently. The surprises it has produced since crossing that boundary have consistently outpaced what any pre-existing theoretical model predicted it would find. The specific mystery at the heart of this story begins in 2017, 5 years after Voyager 1's historic crossing into interstellar space. One of the small number of scientific instruments still functioning on the spacecraft, its plasma wave instrument, specifically designed to detect oscillations in the surrounding plasma, the ionized gas that fills the space between stars, began picking up something researchers had not built into any of their prior models. Before that year, the instrument had behaved largely as expected, detecting occasional, sharp bursts of activity tied to specific identifiable events, most commonly the arrival of a shock wave produced when a large eruption from our own sun, a coronal mass ejection, traveled outward for months or years and eventually slammed into the interstellar medium far beyond the heliopause. Between those known, explainable bursts, the expectation, built on decades of prior theoretical work, was relative quiet, a thin, sparse plasma environment with little happening in the gaps. Starting in 2017, the instrument began detecting something different, a persistent narrow-band emission, a faint but genuinely continuous signal sitting quietly in the data, not tied to any specific solar event, not fading away after days or weeks the way a burst should. It simply continued, year after year, as Voyager 1 carried on deeper into interstellar space. Stella Koch-Ocker, the Cornell University researcher who led the team that eventually identified and characterized this signal, has explained the shift in scientific understanding this discovery represented in genuinely vivid terms. Before this discovery, she noted, researchers had generally imagined interstellar space behaving something like a quiet, gentle rain, an even, low-level background environment punctuated by occasional bursts, comparable to distant lightning during a storm. What? Voyager 1. What 1 actually found, once researchers looked carefully at the data sitting between those known, explainable bursts, was that the quiet periods weren't actually quiet at all. There was a constant low murmur running underneath everything, a persistent signature nobody had anticipated because nobody had ever had an instrument sitting continuously inside interstellar space, for years at a stretch, sensitive enough to notice it was there in the first place. This wasn't a subtle, marginal effect buried at the edge of detectability either. Published in the peer-reviewed journal Nature Astronomy, the research team's findings described a signal sustained and consistent across a distance of more than 900 million miles, as Voyager 1 continued its outward journey, roughly 10 times the distance separating Earth from our own sun. That's not the kind of range you'd expect from a fluke, an instrument glitch, or a coincidental unrelated source of interference. It's a signal genuinely embedded in the physical structure of interstellar space itself, detected consistently across an enormous stretch of the spacecraft's ongoing journey. The research team's conclusions, published with the kind of direct, unusually blunt language that peer-reviewed astrophysics papers rarely allow themselves, stated plainly that interstellar space is not the quiet, uniform void earlier had described. It is turbulent, carrying genuine physical structure at scales ranging from mere meters up to distances measured in millions of miles in a real, physical sense. Alive with motion and complexity that had remained completely invisible to prior science, simply because no instrument had ever been positioned to detect it directly. It's worth pausing to actually sit with what that specific finding represents, because it's easy to read past a sentence like that without absorbing its full weight. Every previous model of interstellar space had been built entirely from the outside, looking in, constructed by capable, serious scientists working from Earth, using telescopes, mathematics, and careful theoretical extrapolation, but never from direct, sustained measurement taken from within the actual environment itself. The very first instrument humanity ever managed to place inside that environment came back and told researchers, unambiguously, that those carefully constructed models had missed something fundamental about the true nature of the universe beyond our own solar system's boundary. And here is where the genuine, still unresolved mystery comes in, the part of this story that separates an interesting historical footnote from something scientists are still actively, seriously trying to solve today. Researchers analyzing this persistent plasma emission have identified two distinct, competing physical explanations for what's actually producing it, and, as of the most recent published research, they have not been able to determine with confidence which explanation is correct. The first possibility is that the signal originates from thermally excited plasma oscillations, essentially the natural, spontaneous vibration of charged particles interacting with their immediate physical surroundings. If this explanation eventually proves correct, it would still represent a genuinely significant discovery, but one that fits comfortably inside existing theoretical frameworks of plasma physics without requiring those frameworks to be substantially rebuilt from the ground up. The second possibility is a phenomenon called quasi-thermal noise, a related but meaningfully different physical mechanism, one that carries information about interstellar plasma density and temperature in a subtly but importantly different way than the first explanation. If this second explanation turns out to be the correct one, it would require existing models of the interstellar medium to be substantially revised, not discarded entirely, but genuinely reworked to account for a physical process. Current theory doesn't fully anticipate operating this way in this specific environment. Distinguishing definitively between these two competing explanations requires either significantly more data gathered directly from Voyager 1 itself, or an entirely new mission specifically designed and built to study interstellar space using instruments purpose-built for exactly this kind of measurement. And this is precisely where the story becomes genuinely urgent rather than simply academically interesting, because neither of those two paths forward is currently guaranteed, and the window for gathering more of this specific data is closing in real time. Voyager 1's own capacity to keep producing usable data of any kind shrinks every single year, governed by simple, unforgiving physics that no amount of clever engineering can fully reverse. The spacecraft draws its electricity from 3 radioisotope thermoelectric generators, devices that convert the heat produced by slowly decaying plutonium into usable electrical current. At launch, these generators produced roughly 470 watts. Today, after nearly 49 years of continuous, unstoppable radioactive decay, that output has fallen by roughly 4 watts every single year, a permanent unrecoverable loss with absolutely no possibility of refueling or physical repair, since no spacecraft in human history has ever been capable of servicing a mission this far from Earth. Of the 10 scientific instruments Voyager 1 originally carried at launch in 1977, Only 2 remain functional today. And NASA's engineers have spent years making increasingly difficult, often genuinely painful decisions about which systems to keep powered and which to permanently shut down as available. Electricity continues its slow, unstoppable decline. That brings the story back to February 27th, 2026, and the specific event that prompted renewed public attention to this entire situation. On that day, engineers commanded Voyager 1 to perform a routine roll maneuver, the kind of rotation the spacecraft has executed without drama for nearly 5 decades, this time to help calibrate its magnetometer, one of the only 2 scientific instruments still functioning on the entire spacecraft. When the resulting telemetry finally crawled back to Earth, arriving more than 23 hours later because that is how long a radio signal now takes to cross the gap between Voyager 1 and mission control, the engineers monitoring the data saw something they had not planned for, an unexpected, unusually sharp drop in power. Sharp enough that if it had continued even slightly further, it risked triggering the spacecraft's undervoltage fault protection system, a self-preservation reflex built directly into Voyager 1's 50-year-old architecture, designed to automatically shut down non-essential systems the moment available power drops below a critical safety threshold. Kareem Badruddin, the Voyager mission manager at NASA's Jet Propulsion Laboratory, has compared this specific fault protection system to a safety net positioned beneath a trapeze artist. It exists precisely so. The mission can survive an unexpected fall. But getting caught by that net doesn't simply mean everything continues normally afterward. It triggers a long, uncertain, deeply complicated recovery process, one that requires sending new, carefully considered commands across billions of miles of empty space, waiting nearly 2 full days for each individual round of confirmation, hoping the entire time that nothing else goes wrong while the spacecraft is left running essentially on autopilot, with no engineer on Earth able to intervene directly in real time. Faced with a genuine immediate risk of triggering that automated safety system, the mission team made a difficult, deliberate choice. They would rather sacrifice a piece of the mission's remaining capability themselves than risk letting the spacecraft's own emergency protocols make that decision for them, unpredictably without human oversight. On April 17, 2026, NASA formally sent the command to permanently shut down Voyager 1's low-energy charge particles experiment, an instrument that had been continuously measuring ions, electrons, and cosmic rays, both from inside our own solar system and from the wider galaxy beyond it, since the very year the spacecraft first launched in 1977. Matt Hill, the instrument's principal investigator at Johns Hopkins University, noted that the instrument's stepper motor had operated essentially flawlessly for nearly 49 consecutive years and more than 8.5 million individual steps, continuing to function reliably even after its supplemental heater had already been switched off years earlier to conserve power, leaving the instrument operating in temperatures as low as 62 degrees below 0 Celsius. Nearly half a century of continuous, unbroken scientific data collection ended in a single afternoon, a deliberate sacrifice made specifically to preserve enough remaining power to keep the rest of the spacecraft, including the plasma wave instrument responsible for detecting that persistent, unexplained interstellar hum, operating for a while longer. Losing that specific instrument carried real, meaningful scientific cost, not merely symbolic weight. The low-energy charged particles experiment had been one of the primary tools that originally helped confirm exactly when Voyager 1 crossed into true interstellar space back in 2012. And it had spent the years since quietly mapping the shifting pressure fronts and particle densities of a region of space no other instrument has ever directly touched. After this specific shutdown, Voyager 1 was left running on just 2 functioning instruments out of its original 10, a plasma wave detector and a magnetometer, both being kept alive on a combined power budget smaller than what it takes to run a couple of ordinary household light bulbs. But the story doesn't end simply with sacrifice and decline, and this is genuinely important to understand honestly because NASA's engineers haven't quietly accepted this trajectory as inevitable without a fight. The same power crisis that forced the shutdown of the charged particle instrument had already set something else in motion months earlier. An experimental procedure engineers have informally nicknamed the Big Bang, designed to restructure how electricity flows through the spacecraft's remaining systems, attempting to squeeze additional usable capacity out of components currently operating below their theoretical maximum efficiency. It's genuinely delicate, high-stakes engineering work, being carried out on a machine with no manual override available, sitting so far from Earth that a single miscalculated command could permanently end the mission, with absolutely no opportunity to correct course afterward. To manage that risk responsibly, the team chose to test the procedure first on Voyager 1's twin, Voyager 2, which has slightly more spare power available and sits somewhat closer to Earth, making a potential failure there meaningfully less catastrophic than the same failure occurring on Voyager 1 itself. Those tests were carried out in May and June of 2026. If the results held up, the plan called for attempting the same procedure on Voyager 1 itself no earlier than July 2026, a narrow conditional window that opened specifically because of the crisis this February maneuver had exposed. Here's the detail that gives this entire effort real, tangible stakes rather than remaining purely abstract engineering trivia. If the Big Bang procedure succeeds on Voyager 1, there is a genuine, real possibility that the low-energy charged particles instrument, the one just sacrificed in April, could actually be switched back on. Matt Hill has been honest and direct about both the hope and the uncertainty involved. The team, he explained, is holding out hope that this latest plan could power the instrument back up, allowing scientists to continue learning whatever surprises still wait in this distant, largely unexplored region of space. But he was equally candid about the genuine limits of what anyone can currently promise. The engineering team, he noted, has built up a genuinely impressive track record of performing what look like small miracles to stretch the spacecraft's remaining power supply further than anyone originally expected. But he was careful to add an honest, sobering qualifier. Eventually, that streak of small miracles will end. It's worth stepping back at this point to place the persistent plasma hum discovery within the broader pattern of surprises Voyager 1 has produced since it first approached the true edge of our solar system, because the unexplained signal detected since 2017 didn't arrive in isolation. It followed years of earlier surprises that had already forced scientists to reconsider what they thought they understood about this specific region of space. Starting around 2010, roughly 2 years before the actual heliopause crossing, Voyager 1's instruments began recording something existing theoretical models simply hadn't anticipated at all. The outward velocity of the solar wind, the constant stream of charged particles blown outward by our sun, had slowed to essentially zero, sitting in an unexpected stagnant equilibrium that nobody had predicted a spacecraft would encounter at this specific point along its journey. Stimatios Kremigis, a physicist at the Johns Hopkins Applied Physics Laboratory who worked extensively with this data at the time, described the genuine uncertainty this created among the mission's own senior scientists in blunt, memorable terms. This boundary, he explained, had caught everybody by surprise, because not even a working theoretical model existed that could predict interstellar gases mixing with solar wind particles moving at nearly zero velocity in the specific way Voyager 1 was actually recording. NASA's own science team eventually gave this strange, unpredicted region 2 increasingly evocative names as they continued to study it. First, in 2011, they described it publicly as a kind of cosmic purgatory, an in-between zone where the outward push of the solar wind had calmed to almost nothing, and where energetic particles native to our own solar system appeared to be leaking outward into interstellar space even before Voyager 1 had definitively crossed any officially recognized boundary. Then, in 2012, as the picture sharpened further, the team introduced a second, more specific term, a magnetic highway, a region where the sun's own magnetic field lines had become directly connected to the magnetic field lines of interstellar space itself, creating an open, unobstructed channel that allowed particles to flow freely in both directions along connected magnetic pathways. Edward Stone, the mission's project scientist at Caltech since 1972, was refreshingly direct in describing exactly how far this specific region had diverged from anyone's genuine expectations. The new region, he stated plainly in a public briefing at the time, isn't what we expected. But we've come to expect the unexpected from Voyager, he added, a phrase that has proven across the years since to be something close to the mission's own unofficial motto. When Voyager 1 finally did cross the true heliopause on August 25, 2012, the actual moment of crossing produced yet another layer of genuine surprise, one that took an entire additional year of careful analysis to properly confirm. Because Voyager 1's own dedicated plasma science instrument, the tool specifically designed to directly and unambiguously measure solar wind density and confirm this exact kind of crossing, had actually been damaged years earlier, back in 1980, during the spacecraft's flyby of Saturn. Scientists couldn't simply read a single clean measurement to immediately confirm the historic moment. Instead, they had to painstakingly reconstruct it using indirect evidence gathered from Voyager 1's other still-functioning instruments, tracking a sudden spike in cosmic rays arriving from beyond the solar system alongside a simultaneous, corresponding drop in particles native to our own solar system. Confirmation ultimately arrived through a fortunate, almost accidental event. A coronal mass ejection that had erupted from the Sun back in March 2012 finally reached Voyager 1's position more than a year later, in April 2013, and the resulting disturbance in the surrounding plasma allowed the spacecraft's still functional plasma wave instrument, the same instrument responsible for the persistent hum discovered years later, to calculate electron density directly. Don Gurnett, the University of Iowa physicist who ran that instrument for decades, later described the moment his team actually saw this specific confirming data arrive with genuine visceral excitement, recalling that the team literally jumped out of their seats when they saw the resulting oscillations, because the readings showed conclusively that the spacecraft was sitting inside an entirely new physical environment, one matching theoretical predictions for true interstellar space, and totally distinct from anything the spacecraft had measured while still inside the solar system. At the boundary itself, Voyager 1's instruments also recorded particle temperatures reaching approximately 30,000 degrees Celsius, a genuinely violent, energetic reading that no existing model had predicted for this specific transition zone, some researchers describing the region using language evoking a literal wall of fire, a real physical zone of extraordinarily energetic charged particles concentrated right at the boundary of everything our solar system contains. Voyager 1 also detected a second, equally unexpected finding at this same boundary. Rather than the sun's magnetic field and the wider galaxy's magnetic field remaining cleanly, distinctly separate the way decades of prior theory had assumed, the two fields were found to be genuinely connected, interacting through a real physical process called magnetic reconnection, evidence that our solar system and the surrounding galaxy exchange real, measurable energy across this boundary in ways no model built before this crossing had ever anticipated. Even years after the initial 2012 crossing, this general region of space kept producing fresh anomalies nobody had fully anticipated in advance. In 2020, Voyager 1's magnetometer registered a sudden, unexplained jump in the intensity of the magnetic field embedded in the surrounding interstellar plasma, an event scientists eventually connected to a genuine physical mechanism, comparing it to a piston, with surges of plasma originally streaming outward from the sun slamming against the outer edge of the heliosphere and generating pressure waves that continued rippling onward through interstellar space, compressing the plasma out there and intensifying its magnetic field years after the original solar disturbance had first occurred. More recent research, published in May and July of 2026, has continued tracking additional ongoing shifts in the same magnetic environment, describing what researchers call a magnetic hump, a sustained, multi-year disturbance first detected in 2020, whose specific effects on the surrounding interstellar magnetic field direction have continued slowly evolving in the years since, with the precise physical trigger and full chronological sequence of these changes still by the research team's own explicit acknowledgement, requiring further, ongoing investigation. Taken together, this entire accumulated body of evidence tells a remarkably consistent, honest story about the genuine limits of theoretical prediction when it comes to environments no instrument had ever directly measured before. Careful, rigorous, peer-reviewed science, built by extremely capable researchers who, using every available indirect tool at their disposal, still managed to get significant, specific details about this boundary and the space beyond it meaningfully wrong. Not because those scientists were careless or unskilled, but because no amount of theoretical modeling from a comfortable distance can ever fully substitute for an actual physical instrument sitting directly inside an unexplored environment, measuring real, unfiltered conditions in real time. Voyager 1 provided exactly that kind of irreplaceable direct measurement again and again across more than a decade of continuous operation in a region no other spacecraft has ever reached. So here's where this genuinely, honestly leaves things, grounded entirely in peer-reviewed research and the direct, on-the-record statements of the scientists who have spent their careers studying this exact spacecraft. Since 2017, Voyager 1 has been detecting a persistent, structured plasma signal in the space between the stars, a genuine, statistically robust finding published in Nature Astronomy, one that broke decades of prior theoretical assumptions about how quiet and uniform interstellar space should actually be. Researchers still cannot say with full confidence whether this signal represents ordinary, if genuinely interesting, thermal plasma oscillations, or a different physical mechanism, quasi-thermal noise, that would require meaningfully revising existing models of the interstellar medium. Settling that question requires either substantially more data from Voyager 1 itself, or an entirely new mission purpose-built for exactly this kind of study, and neither option is currently guaranteed. In February 2026, a routine calibration maneuver nearly triggered an automatic emergency shutdown, forcing NASA to permanently sacrifice one of the spacecraft's last remaining instruments in April, while simultaneously accelerating an experimental, high-risk power-saving procedure that might, if it succeeds, buy Voyager 1 enough additional time to keep this specific unresolved question open a little longer. Engineers currently project the spacecraft's remaining instruments will lose enough power to function at all sometime in the early 2030s, at which point this unique, irreplaceable window into the true structure of interstellar space will close, likely for an entire generation, since no replacement mission capable of reaching this same boundary currently exists or is funded, and even one launched today would need at least 2.5 decades just to physically arrive there. That is not manufactured drama built around an exaggerated headline. That is the honest, current, genuinely unresolved state of one of modern astrophysics' most quietly persistent mysteries, still being actively investigated by real researchers using data gathered by a machine that was only ever designed to survive 5 years, and that nobody, least of all the engineers who built it in 1977, ever expected to still be teaching us something new and something we genuinely cannot yet fully explain nearly 50 years later. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists have measured, admitted, and are still actively working to understand, rather than exaggeration, hit subscribe and turn on notifications, because there's clearly more of the real universe left that our best models simply haven't caught up to yet. Drop a comment telling me which explanation you think is more likely, ordinary thermal plasma physics, or something that genuinely forces scientists to rewrite their models of interstellar space, and share this with someone who still thinks the mystery of what lies beyond our solar system was already fully solved before Voyager 1 ever got there to check for itself.